Alright, time for another draftphysics.com, debatephysics.com also. But again, the debate, lacks completeness. Yeah, we'll say that. So the Dispar guy has repeated the free momentum experiment, which, okay. I mean, this is a thing, okay? I'm just saying, it seems he could do it without even coming close to being frictionless. I mean, just do it in the crew, almost as bad as just banging two wooden blocks into each other. And he's got perfect results. So, yeah. So I'll show a little bit of it, but I mean, it's, uh, not exactly kind of experiment. So what he doesn't do to just prove that his experiment's working correctly is just bang the one mass cart into a one mass cart or a two mass cart into a two mass cart and see if he can elastically put all of the energy in the other cart. That the spring thing is working, that the timers come somewhere. I mean, obviously his timer should be way, the second cart should get a substantially lower amount of momentum merely because there's so much loss in his system. The friction, even for just 10 centimeters, is going to be monstrous. Anyway, and you'll see that. So I'll just play a little bit of it and you get the idea. As far as you can get from frictionless as possible, pretty much. I mean, you can see the carts barely go anywhere. Uh, you know, and so we don't get to see much here. I don't know how well he's aligned the spring to the contact point. Maybe that's stealing a little bit of energy from the first cart because he doesn't have it aligned properly. Who knows? There's probably an explanation, but you can't see enough details. You certainly can't do any frame rates on it. Now, you could just look at it. You can say, okay, well, watching it, you know, what's my impression? That doesn't look very fast, but it's hard to tell the difference between three quarters and, two thirds and one. So, does it look half as slow? Yeah, it sort of looks that way, but who knows? Well, anyway, so it's another, I would call another noise experiment, just because of the fact that we saw no um, standardization, any evidence of the, whatever you call that, a demonstration just for the purpose of showing that the hardware is working correctly because a result we all agree on and it's quite predictable, that is the complete exchange of the energy was tested, and so we know that both things are reading the right velocities and blah blah blah. So we don't have that, so there's nothing to correlate it to. And so we just have to trust that he's pressing the right buttons and doing all this crap correctly. And sorry, I don't do that. But anyway, this is interesting. I mean, this, you can isolate this in ways that make it understandable. In my opinion, that both systems work if you contrive a way of explaining them. You can make them both seem logical, I suppose. I think. I don't know. See, it just part of me just says no. There's just no way you can ever make this make sense. But anyway, so I've argued that there's only two things, and there's only really one source of energy in the universe, and that's expansions and contractions. Okay, so something either gets bigger or something gets smaller, and that's how energy is released in the universe. So all the energy is released in the universe through this process of something that already had the energy put in through compression now expands, and it expands in both directions. And so you could argue that two explosions is really four units of momentum. That for any explosion there's really two momentums, one momentum going this way, one momentum going that way. Alright, now obviously two explosions would be two that way and two that way, so that would add up to four. Alright, now where this goes sideways, in terms of, maybe we could agree on that part, is when they apply it to gravity, because gravity is just a stream. Okay, gravity is just one side of this energy equation. You don't see the other side. You didn't see the compression that added to the expansion that caused the pressure that's moving some object. all you have is this part of it. So you only have one part of that energy equation. You don't have any thing that's being pushed against in the other direction and any energy going in the other. None of that's part of what a water wheel is doing. I mean, a water wheel is clearly taking a stream, degrading its energy, making it move slower by making the wheel turn. So all the energy you took from here goes into here, all the momentum. So again, we have to be careful how we use words. So it conserves the momentum. It conserves this way because that's the only way that's in this mechanism. There's only one way in the mechanism, and all you're really doing is, no matter which way you're taking it, you know, obviously you could argue the wheel turning this way means it's, you know, if half the wheel's going this way and half the wheel's going that way. But as turning energy, you're going to be taking it this way. So in a sense, yeah, well, it's hard to turn that into an equal and opposite. So the argument here is that you can't use the dynamics here that give you 4 aren't going to give them to you here. Okay, and in gravity, gravity's like a stream. All right, and so it's just going to be about how much time you spend in the stream. How long does the stream have to work on you is all that's going to decide about how much energy you're going to have to resist. So you can't change the resistance of the energy. Now, water streams go at a much slower speed than the speed of light. So let's understand that at the speed of light, you can't really change how much, you know, you're never going to be going as fast as the speed of light. So it's not going to be relevant how fast the force is. You know, it's, from our perspective, it's an instantaneous amount of force per unit of time. It's a certain amount of force that will be in this envelope you're going to be in that amount of time. Okay, and that's all there's going to be. It's a certain amount per unit of time. It's 9.8 meters per second, as I pointed out. Oh, damn it. A lot of failures this morning. Okay, I did the other video and I forgot to type. I did the pausing wrong. And alright, so there's the explosion. Here's the little thing I said, see, this is the only part that you're doing with a water wheel. This is the only part of the energy you're seeing. You're just seeing the stream part. It was already created by some other mechanism, and you're just getting this one unit of energy in one direction, and all you can do is take some of that direction away. You can make less of it go that way by taking the energy, absorbing it. And that gravity is doing the same thing as the argument. So the idea is that if you're only in the gravity 2 units of time, you can only collect 2 units of the 9.8. And obviously if I make the unit a half second or I make the unit a millisecond, it doesn't matter how long I make the time unit duration. Newton gave you the example for 1 second. Okay, he could have made it 19.6 per 2 seconds. He could have made it 4.9 for 1/2 second. You could have made this ratio any other ratio, but this is the ratio, 9.8 to 1 second. And so that's all you're going to get is 2 units of pushing. Okay, and the fact is that half your velocity will happen here. You'll be going half the speed here, and you'll do this whole distance, and you'll only gain another half to your speed. You won't gain per foot. You'll gain in these bigger increments. And the same thing going against gravity. This first part, you'll only start going half as fast when you're going this last quarter of the distance. So you get the 3 units here, okay, and it'll be the same work as the 1 unit here, the same amount of loss to your velocity. So clearly there's no correlation between this 4 thing, 2 units equals 4 units. No, it's only time, okay, and it's purely 1-to-1 in terms of what it's going to give you. Alright, so that's the beginning, okay, is that's what I'm arguing. This is how energy is created, okay, in these both way thing, but energy absorbed is only one side of that equation. Most of the absorptions are taking place by tapping some stream, like photons coming from the sun or some other thing. You're not being affected by the light going the other way, you don't have to compensate for it. You're just dealing with a pressure that's going to hit you. Now, their idea is that if we put springs up that could reflect photons, that we could double the amount of energy the photons, the pushing power of the photons. So let me draw that, because that doesn't sound very realistic. But all you need is a spring to double it. Alright, should have hopefully hit the right button. I don't want to do this video a third time. Anyway, so yeah, let's go with the spaceship again, and we'll show how, yes, their theory, it works, okay? It does in fact work, but it does some curious things, okay, in terms of not making sense. So let's say I have an explosion. So I've stored some pressure, and I'm just going to explode and release as an expansion. And all I'm going to consider is the momentum going in these two directions. I'm just going to ignore all the other motions because they'll cancel out anyway, blah, 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 blah. Alright, and so that's all I have. So I have momentum. I have little bits of stuff, little particles going at speeds, and they're going to hit the side of the ship. So if I let them hit this side inelastically, sticking, so their momentum goes into, is absorbed by the ship. Okay, so let's just say that equals 100 in terms of a momentum. That's what hit the ship, 100. Now if I put a spring on this side, okay, so let's just convert this into an object. Okay, so it'll simplify things. This is an object moving with 100 momentum. This is an object moving with 100 momentum. So I put the explosion in a gun, and I fired the gun, and this is what it produces: 2 equal bullets, a zip gun. Okay, and I got equal shit going out both sides. All right, the 100 hits here. It can only give it 100. Can't give it any more. That's it. So it's 100 absorbed by the side of the ship. The two have stuck to each other. And this, we'll just say that for the sake of the argument, let's see how to say that. Well, the momentum is the momentum. Okay, we know that experiment's pretty reliable. That if I bang things in, they stick, they leave with the momentum conserved. That's a Professor Lewin experiment that we can agree on. Okay, or other people have done it. But if I put a spring on this side, a curious thing is going to happen, right? I'm going to give this side of the ship, okay, 200 momentums, and I'm going to reflect the 100. So if this is heavy, we know that if it's 1/2, then I'll get 133. So at half the if I make this twice as heavy, this side of the ship is twice as heavy as the object it's going to hit, the hitting object. So we know this is really heavy. The spaceship is really heavy, much more heavy, and the maximum I can get is the 2. So I can't go any higher than that. So it doesn't matter. Once I make it so it doesn't move, I make it so it absorbs the full 200. So we know this side of the ship absorbed 200 in momentum, and now it's bouncing back with 100. So now at least we'll have the same hitting here again, right? Because this is the sticky side. So I stuck 200, okay, and I have 200 here. So yeah, it works. Okay, but the part that doesn't work is, what do you mean? You mean I have 200 amounts of pressure hitting the ship when I only started with 100? Somehow I doubled the amount of energy the explosion had, okay, merely because I put a spring here. This spring doubled the energy inside the spaceship. The pressure. Because now I'm stuck with the 200, right? There's no, if I put a spring here, okay, then I got 200 here. So I have 200 bouncing back and forth, right? Because I'll get 200 in this direction, and then I'll send back 100 this way, and they'll hit this side with 200 again, and I'll have doubled the pressure inside the ship. But I did start with 100 this way, and I did start with 100 this way. So technically I did start with 200. So in that sense, okay, it sort of makes sense, but it doesn't make sense on this first impact. That's the part that doesn't make sense. Because what if? Well, let's just do the what if. You know, since I'm here, let's do it. Okay, so I don't have a spring here. This absorbed the 100. I bounce it off here. I get 200 going this way. And then I open a hole in the ship here and just let the 100 fly out over here. Okay. So now we're done. There's no other action inside the ship. I've released the energy. So I have the initial explosion hit with 100. I put 200 over there, and then I let 100 out. So it didn't hit the ship. Well, that's just the other 100 that'll move the ship, so that'll be just the exhaust. So it does work. There's no, I won't argue that you can't make it work in a closed system. But it's still, yeah, it sort of makes sense that, okay, you have two hunks of momentum going 100 inside the ship. So the walls of the ship should feel 200 because, frankly, it's going in both directions, right? So if I convert it into one direction, but it's not in one direction. It's the part that still I can't. I'll pause and see if I can figure out how it could possibly be converted into one direction, because I'm not seeing that. Alright, I guess I'll just stick with the basic argument. So we have two different experiments. So let me get rid of all this superfluous stuff that just confuses it. Alright, so with the spring, I end up with 200. I mean, 100 this side hits with 200 momentum. Alright, so MV is 200 here, and this side eventually will be at 200 once the reflection happens, and I hit this side again, the sticky side. I'll end up with another 100 here, okay, for 200. That's with the spring. Without the spring, okay, I do the explosion, and I just have 100 and 100. So somehow without the spring, I only have 100 momentum pushing in the two directions. So if I did open a hole here, right, this side, well, there's only 100 moving over here. Okay, well anyway, let's see what happens. Alright, so if I let this go out, it's 100. If I let this go out, it's only 100. And I'll have 200 that way. So, okay. So if I let the initial 100 out, then it's just 100 turning, okay, because this side's going to hit, this side of the ship's going to get hit. I guess, you know, you have to think of it at the top of the ship, because you obviously do it at the bottom of the ship, you're going to turn the opposite direction. Well, anyway, you have 100 turning, okay, and it's that way instead of, you know, the other way. But anyway, so it's 100 units of turning energy. All right. Now, if I let the initial 100 out here, so let me erase this. So I let the initial 100 out, and then I hit this side with 200, and I have the 100 reflecting, and then I bounce it off a spring. It's going to hit this wall with 200, and so that's going to be even, back and forth with the 200. So that works, I guess. Alright, well, it's going to be needing some more argument. I'm just saying the clear difference between these two numbers, okay, with a spring and without a spring, doesn't seem to make any sense to me. Okay, so I'm just saying on the face of it, that doesn't make any sense. But the only way you can get the 200 is to hit the surface, with a spring. And then you're still back to 100 going the other way. So you hit with 200 and you reflect with only 100. And if I let this side reflect, it's only going to reflect, it's only going to produce 100 this way. And so if I open this side, it's only going to be 100 coming out. So it's still the same amount of exhaust. So it does work, but I'm still dubious. And well, the real takeaway point is that you can't compare these explosion sources where you have a explosion in a closed system to gravity, because gravity isn't an explosion in a closed system. It's a stream of energy. It's already just doing the one side of the equation, and you're never going to get to the other side of the equation. You're never going to see the energy on the other side of the universe. All right. Now I'll take a pause and see if there's anything else to say. Yeah, I'll give it more thought. But I just don't know. Again, every device has to fail at conserving momentum. So I'm just saying the only way you can't capitalize on this extra motion in a direction would have to be that there is no such device that can ever convert the energy from something moving slow into something moving fast. That you never conserve the momentum, ever. No device will allow you to conserve the momentum. Okay, yeah, that would be the argument. Alright, so I'll go to the twice the fuel to go twice as fast argument. Alright, because that one seems so obvious that it doesn't take 4 times the fuel to go twice as fast. That's can't be true. It isn't true. It doesn't work that way. So we're back to the argument that the explosion is really 2 elements of force, and you're only seeing one side of that equation. So here's your unit of energy, your expansion, especially in the case of rocket engines. That's all you have is the explosion, the expansion. You're using the expansion of chemistry in the chemical atoms to create your thrust. And the fact is that you're just sitting here saying, okay, I collected this much from 1 unit of energy. You're only collecting the stuff in this direction. You can't collect the stuff in that direction. So that's understandable. And then likewise, the second unit of gas, the second gallon of fuel, is just going to do the same thing. It's just going to push you again with the same force, just like gravity would. And it's just another unit of force, another unit of acceleration, and it will just increase your speed from, say, 9.8 here to 19.6 here. Okay, and it's only going to take 2 units of fuel. But half the fuel is obviously doing stuff in the opposite direction. So obviously half the fuel isn't getting into the object. Now if you get all the energy into the object, okay, then you could further increase, but there's no way to do that. You can't make this go that way. It's not going that way. So, alright, so, and without applying the opposite force to cause that to, frankly stop. We're back to the stopping argument. This plus this equals stopping. It doesn't equal that. It doesn't matter which one comes first. I can't make something twice as energetic. I can only stop. That's the stopping force, to be able to put it back to 0 from this side by applying a force in the same direction that one went. So anyway, I think it's absolutely true. It doesn't take 4 times the fuel, because all you're doing is using only 1/2 of the energy produced by the fuel, frankly. And for each unit, you're just taking that 1 unit. You're not taking 2 units of energy from 1 unit of fuel, 1 unit of force. This is the only part gravity is doing, this side of that equation. This is the only side you're seeing from gravity. and it's the only side you're seeing from your rocket fuel, is this. And it's perfectly one-to-one. So that seems a solid enough point to make. Okay. And let's see how I can relate that to this momentum argument. Alright, so in all honesty, I'm finding this curious. Just because really the problem might be in equating this generation of the expansion into the universe, the visibility of energy. Okay. So whether something contracts or whether something expands, they're both going to change what's in the universe, you could argue. Because the contraction means it's going to absorb energy, and the expansion means it's going to produce it. It's going to make everything in the environment. If I had a vessel and I made an object bigger and smaller, you could understand that the space that everything in here would have to function in would get smaller and smaller, and the smaller space means it would increase its activity, and it would do so in both directions, in all directions. So there's the 2 units of effect for 1 unit of expansion. Alright, and but you can't apply that to gravity. So that's part of this argument, is that their application of these forces as being the same force is where the big flaw is. And that it could be understood that if I had an object, what I'm thinking is if I did have a small object and I could move it the speed of the force, that is the speed of light, the argument I would make is that it has no components going this way. So the faster I make something go in this direction, the less component it can have going in this direction. So, you can understand that something could be standing still and it has an equal amount going this way and an equal amount going that way. And then if I make it go a little faster this way, and then it has a component that's going this way. Those two are opposite directions, obviously, and the only the only motion it'll have is this motion. This portion will be the only portion that's visible. This part won't be visible. This part is equal. So this part is no velocity, and this part is the only portion of the velocity it'll have. So in a sense, you could argue that if I do have an object, and I can make it go as fast as the force, which is it has all of its bits moving in one direction, and then I could have, and I have anything other than that, that it has components going in the opposite direction, that it has more internal pressure. So you could argue that if I could turn it into something you could visually see, right? It could only be that it's going this way this much and it's going this way this much. Well, those 2 arrows add up to this arrow. If I put them in the same direction, because inside the vessel, that's the pressure. So you could argue, theoretically, right, that there's more capacity, okay, in a heavy object that contains both directions. I still can't make them add up to more. I can't put more energy in this object by making more internal pressure. I can just make it make the same again. Alright, well, I have to think through this stuff. There's obviously room for expansion here. This has capacity to increase this arrow, where this doesn't have any capacity to increase, because of the energy stored inside of it, this dead energy. The energy not active. So because it has inactive energy, it's now capable of producing more in one direction by just reducing this arrow. By taking this away, anything moving in this direction away from this, it has to be added to that, but it still seems like it would be linear. Anyway, I'll think on that. There's no point in me doing that at the same time as I'm making the video. Probably no point. All right, well, I'll pause and attempt a sum up of some kind. I'll see if what the comments are. Well, let's not even bother. Yeah. I'm just saying it is surprising. Okay, let's say it's true, and he's gotten his 1 to 2 mass ratio. Oh, okay, that's the carts in this video. It would seem implausible that he could get exactly the correct results with carts that are so incredibly inefficient. So on its face, that's a little dubious. But again, they keep doing this experiment. I couldn't make it happen, but they're making it happen. But anyway, and it certainly doesn't happen in all the other variations of the experiment, but they all have a catch to them. You can have like an air hockey table, and you can move pucks around and bang them in at an angle, and you conserve the momentum. Well, you'd have to be arguing that it's a heavy mass hitting a light mass and a light mass hitting a heavy mass. Relativity says there's no difference. I can apply the energy to either one of the objects. So, how can it be the same? Because clearly it only happens when you're hitting light things into heavy things. You only have this change in momentum. All right. Well, that's probably a good enough point to end, and we'll do some more thinking about it. So, whatever. Yeah. Yeah, we'll leave it there.